pleasure to be here. I feel we are in the mecca of leather chemistry, and it's really a great pleasure and honor. As it was said, I started out my career as a theoretical physicist, but I should quickly forget about it and rather join our first speaker today, Andrew Everett, who said he has very little to do with leather, so I can join him and say that we're very much newcomers to leather, and please consider that when you listen to my talk. So, in order to make this talk in perspective, I have to go back a little bit in history, as my story will revolve around two companies and the research group that I led at the University of Missouri. And what happened about 8-9 years ago, we developed a technology, a tissue engineering technology, that allowed us to make extended three-dimensional biological structures, living structures. Think about a tissue, think about an organoid, and the dream was that one day we're going to print organs, just like a heart. And so this technology, forming those extended biological structures, the way we did it was printing those structures. So today, this technology is called bioprinting. The first company that was mentioned, Organovo, is one of these companies that we launched. We launched it in 2007. It is by now a public company on the New York Stock Exchange. So this is a real satisfactory outcome. And so that I can bring in the leather, let me just show you how this technology works. So basically, what you will see here is there is a printer working up there. On the left, at least to me, is a reality. A cellular structure is being constructed, and this is just schematics. So we have some kind of a template, which is shown up there, and the printer is moving according to that template and laying down the bioink particles, which here on the left, on the right, to me, are little spheroids composed of various cells, and they're cylinders. The white stuff is a cylinder, the blue stuff is agarose, that is just a temporary scaffold material that contains this the cellular material, because the magic happens post-printing, and you could see here on the schematic slide that those bioink particles, in that case the spheroid, fuse together. And that happens post-printing. So the printing is really just a method, a convenient method to deliver those bioink particles, which themselves are small microtissues, and then eventually they fuse. And fusion of tissues is a ubiquitous embryonic morphogenetic process. That's how we come about in the early embryonic stage, and that's what we try to mimic here. So basically, this technology comprises the bioink, the bioprinter, and the scaffolding material. And then biology takes over post-printing. So this is the technology that Organovo uses today to build biological structures, and here is an example. We built blood vessel type structures or nerve grafts, cylindrical structures that I showed you how to build in the previous slide. So that's how it started, and some of those structures have been implanted into animals, and by now there are various kinds of other tissues that we can build, and here's where this, basically this slide is going to demonstrate where this technology is today. So building the heart, the liver, the lung, that's a long-term project. But here is why this technology is so important and relevant today. And that goes back to how we develop drugs. And there are many steps, of course, but there is one when we go from the preclinical animal trials to the human clinical trials, and up to 50% of the drug candidates fail. And the reason they fail is because animal tissues are not the same as human tissues. And so what this technology is doing today is to interface, the preclinical animal trials with the human clinical trials. We take this engineered tissue, we try the drug on them, actually built from your own cells. And so this is called autologous tissue engineering. Takes the cells from the patient, forms those little tissues, tries the drug, which is going to be tailored to your needs, and then if that is successful, there is an indication that it works in human tissues, then you go to human clinical trials. So in principle, a lot of money can be saved by that, and that's one objective. So as I mentioned, nowadays, today we have various tissues that have been formed by this technology, and so the drugs in principle can be tested on various drugs. And Meadow is coming up with the first liver tissue patch that is going to be used by a number of pharmaceutical companies for this purpose. Okay, so this is human regenerative medicine. But once this was underway, we asked the question, if we can build medical grade human tissues, then what else could we do with this technology? We are able now to build tissues. What is else there that this technology can be used to build tissues and then to be useful? And so what came, of course, eventually to our mind is, one is your favorite steak, that is a tissue, and the other thing is your beloved leather jacket. So those are tissues, or at least they were tissues. Those are post-mortem tissues, because they go through all kinds of modifications by the time they get to the consumer, but they start out as tissues. And those are the entities that we can build. So to make the long story shorter, we embarked on adjusting our technology, this biofabrication technology, not necessarily the printing, but our ability to build extended tissue constructs to perhaps building meat and leather. So I'm not going to talk about the meat today, but I'm going to talk about where we are today. Actually, the company was launched in 2011, at the end of 2011, so this is practically the beginning of 2014. So what is where we got in 2 years? There is another aspect of all this activity, and this is revealed by this hidden, well-guarded place, where, by the way, those two products, the meat and the leather, both originate. Now, this is a manicured slaughterhouse. Manicured in the sense, I don't know how many of you have been in a slaughterhouse. I have, and trust me, it's not a very merry place. And this looks much better than in reality. So there is this aspect of sustainability, there is the aspect of environmental damage, health, and ethical issues all come together when we think about perhaps making meat and leather, or engineering meat and leather without harming the environment. So, what if we could do this without harming the environment, with using much less of our precious resources, and without doing harm to the animals? And those are issues that are being raised by everybody nowadays who is thinking consciously about those issues. So, how to do it? Well, if we can do it, then we would also make a big step towards mitigating those problems that environmental implications lead to. 33% of ice-free land today is used for sustaining animals, and for overall agriculture, it's about 70%. So that's number one. We are destroying our water supply system, and by industrial meat production, and we are polluting the environments probably beyond the 18%. Keeping animals is really, it's more polluting for the environment than the greenhouse gases, as we know that well. They produce greenhouse gases, but I mean the greenhouse gases that are produced by, say, by the oil industry. So this is a very serious problem, and here is the process that perhaps can mitigate some of those issues. By the way, I also want to say that right now we are about 7 billion on the planet, and we share that with about 60 billion animals. And by 2050, there will be about 9 billion of us, and there will be 100 billion animals. Those 100 billion animals are competing for the same resources what we need. So just, I'll leave you with this thought. Okay, so how do we do it? So this is the schematics. I'm going to go into some details on some of those steps, but basically we start sourcing the cells from the animals, but not killing the animal. So we just scoop a few million cells by more or less harmless biopsy from the animal. We take those cells, we grow those cells to the appropriate numbers under very controlled conditions in the lab. So sterility is preserved there. There is no chance for contamination, at least most of the cases. And we entice those cells, which typically in this case would be dermal fibroblasts, to produce what they know to produce, and that would be collagen. So they secrete the collagen, we help them, we entice them, we encourage them to produce collagen by various tricks. We collect that collagen in a sheet-like form, and either we put the sheets on top of each other, or we just put more cells on the first layer, and then we grow things in thickness. And then comes basically the engineering step. And I have to emphasize that we are mostly tissue engineers. That meaning that we can do things supercellularly. We know the biology to a large extent, intracellularly, but that's not our primary expertise. We know how to put together tissues and how to put together organoids. And that's what is happening here. So once we have this tissue, because it's still a live tissue, cells in their own collagen matrix, then we have various methods, engineering methods, to bring that to a shape, to a form that could be used by the leather industry. So that's really the purely engineering step at this point, and that leads to this material. I would like to call it leather. I don't know what the real definition of leather is, but it's a leather-like material, and once it is put together to the thickness that a particular consumer would like to use for industry, then come the finishing steps. So I can't lag behind our first speaker, so I'm going to show you one of those samples. What I would like to ask you, there is a sample here. A piece of it is sticking out. You can touch it, you can pull on it, but please be gentle. This is not yet the equivalent of a bovine hide or leather. This is still relatively thin, relatively fragile, but you will see where we are getting with this technology. For sure will give you a pretty good impression. And so this piece has been handled by some people already. So it's not perfect, but what is perfect anyway? So this is pretty good. It's dyed green, so just to show you that we can dye it, and hopefully you will appreciate the experience. Okay, so where do we go with this technology? We obviously, depending on what the specifications of the various industrial partners are going to be, the leather will have to be, or this material will have to be appropriately prepared. Now, just to go into some of those steps a little bit in detail, because there's those steps, the 7 or 8 points that I listed there, because each of them is pretty complex. So to appreciate it a little bit, imagine that you have a few million cells from this biopsy, but if you really need to do something, that you will see that structure there contains billions of cells. So we have to grow, number one, we have to grow those cells. Today, it's happening in cell stacks. It's a special type of tissue culture method to grow cells. But when we really get to industrial scale, production scale, we will have to use massive bioreactors that are coming to the market nowadays, and they can produce billions and billions of cells. So you have to grow those cells, you have to feed those cells, you have to get rid of the waste, and then you have to be able to collect the cells. Then you have to put the cells together so that they can finally produce the material that you're hunting for. And there under the panel 3, you can see one of those sheets, and then you can see 2 of those sheets next to each other. Those are thick collagen sheets. Well, at least we think that they are mostly collagen. And once you have them, you can do 2 things. You can put them on top of each other and then combine them, or you can take one of them and wrap around the mandrel. If you do that, then you increase the number of layers. That's one engineering approach to increase on the thickness. And before you even tan it, you can take that hide, because this is what our cultured hide is, and it's pretty impressive. You can pull on it, you can play around with it, and it has very interesting mechanical properties. And then comes the step, that's where we need your help, is tanning those samples, and that itself is a challenge, because traditional tanning methods do not necessarily apply to this material. And the one that you see there, it was tanned with chromium, but even the chromium tanning was significantly different than what the leather industry, traditional leather industries use. And then nobody is telling us that chromium is the best material to use. Okay, so if you look into this material, you will see abundant fiber structure in it. I have to say that we can't be 100% sure that this is your collagen. It looks like collagen. We have tested it by antibody, but none of the methods that we have used so far necessarily dictates that this is the traditional collagen structure that you will find in the animal skin or eventually in the hide. However, it is an interconnected structure, so when you use chromium or other tannins, you reinforce the structure, and it is already relatively strong. So I work in collagen in a totally different world, purely biology, and the structure, the bundle that you see here, is something that I interfaced many times in my life. So that's why I would think that this is robust collagen. But again, the verdict is still out there. Here's a video that will give you some ideas what this material is. So Gabor, who is sitting there, is playing around with the sample, pulling on it, massacring it, challenging it, and eventually the mutilation steps are reversible, and you get back to where you started from. So again, the properties of this material are not yet the same as that of those of traditional leather, but they are getting there, and they are in fact controllable. In other words, we can provide or engineer attributes to this material that the leather industry probably cannot. So here's our little sample booklet, and this is what we can show. Well, we have now more, but this is something that we can provide to the representative of the industry. And I would probably not reveal you a secret if I tell you that the fashion industry, the auto industry, the upholstery industry are there just interested very much in this material, because it's the ultimately environmentally friendly approach of building something that may have properties very similar to leather. So there's nothing artificial here. I really would like to emphasize that. And people inadvertently refer to this material artificial leather, and then I feel that my blood pressure is going up, because this is not artificial. This is produced by cells. If this is produced by cells, then this is not artificial. It's not necessarily the identical equivalent of the leather that we are used to. But then who says that's the best? So what I really would like to now do is recapitulate what this technology is where is it now, and what is it capable of doing. So the first thing is it's a controlled process from sourcing to the product. You can imagine that everything is done under one roof. So we get the biopsy, and from there on, none of those steps need to be performed outside of our little enterprise. We can do this all in one building, and that is pretty important. No transportation costs, no exposure to various harmful agents, etc., etc. So from everything that I told you follows that this is much more environmentally friendly, and obviously animal friendly. You don't have to kill the animals. Environmental friendly. Just think about what you do when you start your tanning operation. You first have to get rid of the hair. You have to get rid of flesh. You don't have to do that. So what the previous speaker was talking about, how to remove the hair roots. Well, that's a complex process. So apparently there are now better and better methods. But what is the best is not to have them at all. And then you don't have to use those chemical steps. The next that we can think of is what I just said. In fact, that a number of greenhouse operations are not present, and as a consequence, the need for chemicals is much less, and we can proud of ourselves that we're not polluting, at least not to that extent, the environment that is done by industrial leather production. This is a very important thing. We don't need to produce waste at all. I can grow my leather sample to exactly the specification, size-wise, what the industry wants. So somebody working in the shoe industry tells me, okay, well, I need this shape leather so that I don't have any waste. By the way, the shoe industry wastes about 30% of the leather, and the car industry, waste of car industry is up to 50%. So imagine how much we could save, again, environmentally and also financially, if we could just engineer the piece with the shape that is really needed. And there is no reason not to be able to do that. Nothing prevents us to pre-shape the structure that we want to take. Another interesting point is that we can come up with properties that the leather industry simply cannot produce. And I'll give you an example. So bovine fiberglass, ones that are typically used when we want to mimic something that resembles bovine hide, are the only, they produce predominantly collagen type 1. But
But if you look at the young animal, then collagen type 3 is in much more abundance than in an adult animal. And a leather rich in collagen type 3 has fundamentally different properties. It's finer, it's perhaps weaker, but it's a more luxurious item eventually that can be produced out of it. We can take any kind of cell that produce collagen. So indeed what we did, we used smooth muscle cells, the cells that reside typically in your blood vessels, and they produce tons of collagen. But that collagen that they produce is predominantly type 3. And in fact, we built leather samples of that material. And they have different property. They have different property than the one that you built from fibroblasts and predominantly contains collagen type 1. And you can imagine, we can engineer any kind of property. We can make our leather, as one of those samples revealed, translucent, transparent. And the garment industry would be, they're just very excited about such possibilities. Something new, some possibility too. So at the end of the day, what this technology represents is one of those more and more in fashion biofabrication processes that mimic nature as much as possible. So we're trying to build nature-like material, nature-inspired materials. Another one, by the way, would be silk, which bioengineers are working on. Using methodologies like the one that I've presented here. I elaborated a little bit more on bioprinting, but that's not the only approach that is out there. There are now a number of bioengineering, tissue engineering approaches that are used for this exercise. So it's a novel biomanufacturing approach to natural materials. And okay, so just to wrap up my talk, I started out with a vision, printing parts and those organs, and I truly believe that we will get there once, not necessarily to the same heart that you carry in your body, but to something equivalent, built from your own cells, and will perform the same tasks as your heart, maybe even better. And so I would like to end my story with another vision. This is a beer brewery, but imagine that now it's not, we're brewing not beer, but we're brewing cells. And the message I want to convey, look at this facility and compare it with the slaughterhouse. Everything is clean, everything is transparent here, there's nothing hidden. You're allowed to go into this facility, whereas you're not allowed to go to a slaughterhouse. And it's just much more patient-friendly in some sense, or consumer-friendly. You would be much less against perhaps this approach when you see how it produces the material that you eventually either going to wear or perhaps even ingest when it comes to meat. So that's really essentially where we are today, and there's a lot of things we need to do to improve, but I think that the sample that you had the chance to touch, look, perhaps smell, hopefully makes you believe that something like this is possible. So I am an academic, so I have to thank to my students who will do that. This is now becoming a historic image. I can't recognize myself there. A few years back, the reason I'm keeping this is because this is where essentially time-wise this whole activity started. Not with the leather, but the biofabrication enterprise building tissues, and we consider that the leather and the meat as part of that. So many students have participated in this. Not all of them are unfortunately on this picture, on this photo.
We were very generously supported by the various funding agencies, because in academia you wouldn't be able to do that. Without that, unfortunately, those sources are going down more and more, and that's why time is to forget old time and try to go to other sources. So with this, I would like to thank you for